All right, good afternoon, colleagues, and welcome to the third session of our webinar series on longitudinal data. We have dealt with a couple of lessons already, so we dealt with two webinars which were focusing on the managing and the cleaning of longitudinal data. And so today we're going to ease into the analysis of longitudinal data. And just to take us through what we're going to, just the ground rules first. These webinars are recorded and they will be stored as a learning resource. You will have an opportunity to ask questions. So if you can type your questions in the Q&A section of your Zoom app, and we can also answer questions at the end of this session. And these are the topics that we have covered so far. We've covered the introduction to the planning of longitudinal studies and data management. We've looked at tools for exploring and cleaning longitudinal data. We'll get more into that today. We looked at introduction to analysis of longitudinal data. Today we're starting with the introduction to the analysis of longitudinal data, and we'll finish up tomorrow with getting into the more complex analysis of longitudinal data. And as I mentioned before, we do have a toolkit that we are providing, and we've created an R toolkit, and where possible, we'll provide data comparable commands, but this has largely been based on R. The scripts that we provide to also demonstrate how to use R for those of you who are new to these sessions, but we've covered just what R looks like and how you can navigate yourself through R, and as well, we're covering steps for modeling. So in these 2 days, basically, we're not gonna get deep into the descriptive and the inferential statistics and comparing two groups and comparing more than two groups, but just as a basis of practice to analyze longitudinal data, we'll look at these methods. All right, again, just to start us off with the definition and really to emphasize the importance of what we've been talking about and the reason why we focus first on the organization of the data and the cleaning of the data. If you look at how statistics are defined, it includes both the organization and the collection and the organization of the data. Before we get into the analysis of the population characteristics by inference from the population. So those aspects are important aspects that we needed to cover because before we even get to the level that we're getting into now, we needed to understand how we can manage our data, how we can clean our data and prepare those data for the analysis that we're going to perform. And so we're going to deal a little bit with descriptive statistics, which deal with methods of organizing and summarizing data and presenting them in a convenient and informative way. And we'll explain what that means. And then the next level is inferential statistics, which are about making statements about the population from a sample. So generally, you're interested in making statements about the general population from which you're drawing the sample. And so you need to make sure that your sample is representative of the population, or else you're unable to make generalizations of your findings onto the population. All right. And so, okay, this is a repetition. And generally, so the process that we've been following is really looking at the exploration, the cleaning, and today we're looking at describing the data, and we look at making inferences in terms of modeling of longitudinal data. So just briefly again to remind us, we are looking at longitudinal data, which are data that are measured on several occasions. And you may be interested, for example, in looking at the change in a physical dimension in a child, measuring child growth, or in some developmental characteristic, all right? And you may be interested in factors that are associated with that particular change and what may induce that change. And as I mentioned, the change can either be negative or positive. So growth does not necessarily mean a positive increment, but it means that there is a change. All right. Now, within the analysis of longitudinal data, we're interested in understanding within individual change. So how does one individual, what are the trajectories for each individual, but also what are the differences in the changes between individuals, all right? And the key questions that we are trying to address is how does a variable change over time, and whether we can predict differences in changes over time according to the presence or absence of certain factors. If, for example, you're trying to see whether the trajectories that are observed in the individuals or in the groups can be influenced by some factors, by some explanatory factors, how do you then address that? How do you change that? For example, if you're looking at an exposure of exclusive breastfeeding versus non-exclusive breastfeeding, and you follow up infants from birth up to the age of, say, 24 months, and you're interested to see what are the changes in body composition, fat mass, fat-free mass over time. That's what longitudinal data allow us to do. And by asking these questions, we're able firstly to characterize the patterns. And so we'll be able to see how children grow over time and to see the pattern of growth, but also to detect whether there are differences between groups and individuals, and again, to assess factors that are associated with the differences in the trajectories. Now, there are different approaches in terms of modeling longitudinal data. You've got non-parametric approaches and you've got parametric approaches. Non-parametric approaches, especially when you're dealing with growth data, for those of you who are interested in growth data, looking at changes in height or weight over time, you have different models, some which are non-parametric, and they do not hold any prior assumptions about the shape of the data, and you do not need to specify a particular function to try and describe the data. Whereas with parametric data, you have priori assumptions that you have to make about the shape of the data, and you need to specify a function. But they also provide summaries of the trajectories, such as the intercepts and the slopes. All right, now in longitudinal data, as I said earlier, each participant is measured repeatedly over time. And this is just a reminder, revision of the data structures that we have in longitudinal data. Generally, when you're dealing with data, and if you imagine what you will have in a spreadsheet, for example, you will have all the data pertaining to an individual in one row, all right? So whether you're talking about the ID of the individual, say, let's assume is ID number 1, and you've collected a couple of variables. You've collected demographic characteristics, you've collected anthropometric characteristics, and you've collected some clinical characteristics. All of the data for that one particular individual, whether it is at different time points, they will all be in one row. All right. So, for example, if you have got variables which change over time varying variables, such as your height, for example, you will have height 1 in column, say, column C, and then you'll have height 2, which is at a second time point in, say, column, in the next column, column D, and so on, depending on the number of time points on which you've collected your data. In the long format, which is the format that we need our data to be in when we're analyzing longitudinal data, you've got all the data pertaining to a particular variable in a single column, and you've got multiple rows representing data for a particular individual. So if, for example, going back to individual with ID number 1, and you've collected data on 5 time points, all of the data for that individual, all of the data for individual 1 will be in 5 separate rows to represent the time points on which those data were collected. And that allows us then to summarize data according to time point. All of the variables it will allow us to summarize the data according to the time point. And it also allows us to plot the data and to explore the data, as you will see. All right. Oh, sorry, I'm going backwards. So there are 3 types of data in terms of longitudinal data. You've got individual, constant variables, and those are variables that differ across individuals but remain fixed over time for each person. You've got time constant variables, and those are variables that differ across individuals but remain fixed over time for each person. Sorry, this is a repetition of the same type of variable. It's going to be explained in the next slide. You've got time varying variables, and those are variables that change over time. So, for example, if you're looking at individual constant variables, so they are constant among the individuals, and also they are constant over time. All right, let's see what I wrote here. So they remain fixed over time, and yeah, and they do not vary across individuals. So, for example, if we've got data which are collected at different sites in different countries. So you've got South Africa, you've got Namibia, you've got Mozambique, you've got Lesotho. All of the individuals within the country, whether they're male or female, they will have the same country variable, all right? They will have the same country label, all right? And it will be either South Africa, or it will be Namibia, or it will be Mozambique or Lesotho. With sex, it's going to, so among the individuals of that particular country, that variable, the country does not change. But with a variable, for example, like sex, the sex at birth, or the year of birth, the date of birth of that particular individual is going to vary from individual to individual within a particular group. All right, but it does not change over time. Whereas time varying variables are the ones that both vary across individuals as well as vary over time. All right, your height at time point 1 is going to be different to your height at time point 2. So it's important to recognize these variables, because your data will then be clustered within these groups. Now, in terms of, as we ease into how to approach analysis of longitudinal data, we need to think about the different types of variables that we may have in our data set. All right, so broadly, you've got, some people will use numeric and categorical, or some people will use quantitative or qualitative. All right, so but this is all in the context of quantitative research. All right. So qualitative here does not necessarily mean qualitative in the sense of qualitative research. All right. It talks about variables which have got no quantitative quality, but are describing some characteristic in your participants, but can be coded and to be interpreted numerically in quantitative analysis. Whereas you also have quantitative or numeric variables, which include these three different types: continuous variables, count variables, and ordinal variables. A continuous variable, now a continuous variable is one that takes any um, any value within within a particular range. For example, say for example your height in a particular range of adult height, or your blood pressure in a particular range of adult blood pressure. Your blood pressure can take any value within that particular scale. All right. Count variables are simply that. It's, for example, the number of conditions that a particular individual may have. And ordinal variables include variables that are on that are measured on an ordinal scale. For example, where there's a hierarchy. For example, you are looking at a pain scale, for example, that is a rating from 0 or from 1 up to 10, for example. So what is the level of pain? And also, these can also include variables that are measured categorically, such as your Likert scale, which is your agree, um, strongly agree, disagree, and strongly disagree. All right. And then you've got and you can see that there's a hierarchy in how this, if you're looking at your ordinal scale, there's a hierarchy in the levels of in the different levels of this variable, with somebody who is agreeing being different, completely different to somebody who is disagreeing. Or if you look at another variable, if you look at, for example, severity of disease, you're looking at mild, moderate, and severe, with somebody who's got a mild condition being in a way better off state compared to somebody who is in a severe condition. All right. So that's an ordinal variable. In a categorical variable, you do not have any hierarchy. All right. So you are looking at groups, and you've got more than two groups. All right. And describing some characteristic. For example, you're looking at hair color, you're looking at eye color, and you've got more than three groups. Or you're looking at race, or you're looking at race gender groups. You've got white males, you've got black females, you've got black males, and then you've got white females, for example. All right, so in that analysis, you've got four groups, and there's no hierarchy, there's no inherent hierarchy between in the groups, in how the groups are ordered. They're just assigned codes, maybe according to alphabetical order or whatever. All right. And then you've got nominal variables, which usually take up which will usually take up two, a binary code is either a one or two, a yes or a no, or dead or alive. All right. And so, and all of these variables influence the approach that you're going to take in terms of summarizing these variables. All right. So with continuous variables, you will summarize them. You can summarize them with either the mean or the median or the mode, same as the count variable, and with ordinal variables, as mentioned earlier, some of them can be treated in a numeric manner, but others can be treated in a categorical manner, all right, or and in a qualitative manner. And so they can be summarized as medians and modes, or they can be summarized, if you're treating them categorically, you can summarize them as percentages, whereas the categorical variables or the discrete variables can only be summarized as proportions and frequencies. All right. So these are the different types of variables. All right. But for this webinar, we're purely going to be focusing on continuous variables in terms of the modeling that we're going to be performing. And in terms of the analysis that we're going to be performing, we're looking at a continuous outcome. So that would, an example of that would be your height. If you've got a different outcome, for example, like your binary outcome, then you're looking at something like your logistic regression. If you've got a discrete outcome or a categorical outcome, you're looking at multinomial regression. And if you're looking at an ordinal outcome, you're looking at ordinal regression. All right. Now, when in terms of best practice, when we analyze data, it's always good as a first step to try and make sense of the data that you have. And one of the ways in which what we make sense of the data is describing the data and using these descriptive statistics that I've just mentioned. And we are interested in summarizing the data in a manner that ensures that important features are not lost, and that includes the shape and the type of the variable. And as an example, in terms of how you ensure that you do not lose the important features of the data, you cannot summarize a categorical variable as a mean, for example. And you may be surprised. This is something that has, one does come across, all right, where if you've got a variable for gender or the sex at birth of the child, one would want to take a mean of that. That is not meaningful. You cannot have, an average sex as an example, all right? So the summarization that you apply must be informed by the type of variable that you're dealing with. So this is what I mean here. So if you are dealing, as I showed in that flow diagram, if you're dealing with categorical variables or with nominal variables, you can only summarize them with percentages. Whereas if you're dealing with numeric variables, you can summarize them with means or medians. But also the issue of the shape of the data, we will use certain graphs to inform us of the shape of the data, such as your histogram, for example, that will tell us whether we're summarizing those data as a mean or a median. And from that, it will tell us the type of analysis that we will perform. For example, if your data have got a skewed shape and you're dealing with a small sample size, you are advised to summarize those data using a median. If you if the shape of your data is not skewed, it follows what we call a normal distribution, as you will see later on, a bell-shaped symmetric distribution, then you can summarize those data using a mean and a standard deviation, and using the parametric methods of summarization as well as inferential statistics. All right. So in our summarization, it is important to compute summary values that represent both the location and the spread of the data. It is not enough to know just what the mean is. Also important to understand what is the spread, because it is possible. I think I do have a slide later on. It is possible to have a situation where you've got equal means, but the spread, meaning the average distance of the variables from the mean, is different in the two groups. And the location, also obviously you want to see if you're dealing with two groups, for example, if they have got the same location. All right. So when we're making sense of this data, obviously you can't make sense of data when you see them in a spreadsheet, and we then compute these summary values that adequately represent the location and the spread. And before anything, we explore them through plots. All right. Now, there are different measures of location that we apply. As I mentioned earlier, we've got the mean, and there are different types of mean, but we're going to focus on the arithmetic mean. And we've got the median, which is the measure. So a mean is a sum of all the values divided by the number of values. All right. So that gives you a sense of the average. And the median is a value that is in the middle of the data set when that data set has been ordered in ascending order. And the mode is the most frequent value in a particular data set or in a particular variable. Now, measures of spread include measures like standard deviation and variance, which measure the average distance from the mean, and this is accompanied with the mean. So whenever you're presenting the mean, you will present it with the standard deviation. The standard deviation is simply the square root of the variance. And the interquartile range is the range between the first and the third quartile of your data, and it covers, 50% of the data in your data set will lie between the first and the third quartile, and the range encompasses all the data points in your data set. And I'm not going to get into detail about how to work out about these equations, but this just tells us that you sum up all the values and you divide them by the number of observations, and it is suitable for data which are normally distributed, and it is sensitive to outliers. I will make a demonstration later on what we mean about this by this. And so the median is a value in the middle of a data set, of an ordered data set, and it is suitable for analyzing or for summarizing rather data which are skewed, as it is not largely affected by outliers. Now, if, for example, we consider, I'm going to move out of here a little bit. So if we consider this data set, all right, and this is just, for those of you who are coming in for the first time. So these are the scripts that I mentioned earlier that will be provided as part of this course. One, an introductory script, one on preparation of data, on management of data, and on cleaning of longitudinal data. And today's one is focusing on the analysis of longitudinal data. And parts of it will be covered today, and the next parts will be covered tomorrow. So I just create a new script, for example, and I create this data set. For example, I can run this. So I've got values. If I just take these values, 5, 3, 8, 4, 1, 5, 0, and 6, all right, it's the same. If I try and find the mean and the median of these values by just running this code here, you will see that the median and the mean are quite similar, all right? And the results are shown here in the console, which shows us the results of everything that we are running, all right? Now, just to highlight the point that I meant when I said the mean is sensitive to outliers, whereas the median is less sensitive to outliers. Now, if I create a new data set and I call it B, and I add an outlier to that data set, and I then compute the mean and the median for the new data set, we will see the impact that this new value has on both the mean and the median. Now, if you look at the results for this vector A, it is 4, the mean, and the median is 4.5. And just as a, by the way, if you want to thumbs up whether there is a difference, there is your data anomaly distributed or not, you look at the difference between your mean and your median. And if your mean and your median are very close, then that means that your data are normally distributed. So, it's just if you just want to have a visual way of assessing whether your data are normally distributed or not. All right. Now, I've introduced an outlier in this particular case, and let's see what impact it's going to have on the data or on the summaries. All right. Now I've got a vector called B, and the mean for this vector is now 9.1. So it is 2 times what the mean of vector A is. But let's look at what the median of this new vector is. It's only gone up by 0.5. So you can clearly see that the median is not affected largely by this outlier. All right. So when you're summarizing your data, it's important to explore these shapes so that you can see, what the impact of different values of different shapes is. All right. So this is what I was supposed to have done. All right. And I've demonstrated how the mean and the median respond to the outlier. All right. Now, one of the things that I remember I said you're not only interested in understanding and summarizing the data with the measure of location, but also with the spread. All right. And for parametric analysis, analysis, yes, you can use a variance or a standard deviation, which is an average, which measures an average distance of each value from the mean. Now, if you were to go ahead and subtract every value from the mean without squaring it, this would be a sum of 0. All right. So in order to try and avoid that, not to try, but in order to avoid that, to get an average of 0, which will then be 0 divided by your sample size, minus 1, which is undefined, you need to square these deviations. So and then once you squared the deviations, you will then generate a square root, which will take you back to some form of an average distance. All right. So as you can see here, the standard deviation is a square root of the variance. So we first work out the squared deviation of every value from the mean. So this x bar is the mean, xi is the value of every individual. It can be the first individual. If you've got 10, I ranges from 1 up to 10. All right. So it can be x1 minus minus the mean. It can be x2 minus the mean, and you add up all of those squared deviations and you divide them by n minus 1. All right. And the reason why you subtract by n minus 1 is because you've already used up a parameter here, a parameter of your data in the mean. All right. So you're accounting for this one parameter that you have used in your data. Now, in terms of the assessing spread for non-normally distributed data, the options are your interquartile range, and you present the data above which. So the first quartile is a point at which above which 25% of the data, 25% rather of the data lie below the first quartile, and 25% of the data lie above the third quartile. And this equation here can help you to identify values which are outliers in your data set. And again, to work out, to observe the standard deviation in your, I'm not going to run this, but this is the code that you can run to assess the standard deviation of your data set, and it's simply SD. And if you want to generate the interquartile range, you can use this this code here, or this function called quantile. All right. Now, I mentioned that it's important to obviously to assess the distribution using you can use your histogram and to assess the distribution of the data. And the histogram is generally a symmetrical bell-shaped curve. And in this particular case, the mean, as I mentioned earlier, when your data are normally distributed, your mean and your median will more or less be the same. And you've got different types of skew, where some data are positively skewed, meaning the long tail is to the right, or negatively skewed, meaning that the long tail is to the left. For example, in particular situations where you've got a condition that largely affects elderly individuals, your mean age will be high, whereas your biological characteristics usually take up a skewed distribution with a positive skew. All right. And this just gives us an indication of what the relationship of the mean and the median is in relation to, in the different types of distribution. And as I said earlier, I mean, we saw in the example that I demonstrated that when you've got an outlier, and this is a positive outlier, I added a value of 50, which was way higher than the values that existed in the database. You can see that it increased the mean. So the mean is larger than the median. Whereas if I had added a negative value, or if I had high values and I added a much lower value as an outlier in the data set, it would have pulled the mean to the left. All right. I demonstrated last week how you can use a box and whisker plot to observe your data and to identify outliers. And I demonstrated this equation that helps you to identify values which lie below the first quartile minus 1.5 times the interquartile range, which is the difference between the first quartile and the third quartile. So the values that lie below and the values that lie above the third, above the third quartile. And this is the median here that we see in the middle. All right. Now, in terms of one of the important elements of observing, or rather exploring longitudinal data, is to perform scatter plots. This just shows a scatter plot of height versus age. So you've got age on the x-axis, and the group in this data set, which you will see shortly, it is a data set with both males and females, and you've got data, and you can see the blue, the light blue dots being those of the girls, and the, say, pink dots being those of the boys. And these are longitudinal data from the age of 5 to the age of 11 years. And you can see clearly the plot, how this date, the pattern rather of increase in this variable. Now, one of the nice things, or one of the important plots that one should run when dealing with longitudinal data is what we call growth plots, where you can see how each individual, can demonstrate each individual pattern. All right. And so, for example, you can see this one particular individual is way above or is growing more superiorly compared to growing superiorly compared to the rest of his peers. So this is a boy. So he's growing, way higher. His height is above that of his of his peers between these ages, and it's going to demonstrate to you, and this is helpful to see whether there are patterns which are not expected within the data set. So I remember I was dealing with a data set, for example, of intrauterine growth. So this is where we're measuring they not these, I mean, the researchers in this particular study, they measured biparietal diameter, they measured femoral length, they measured head circumference, and then we estimated fetal weight as well, and abdominal circumference as well. And you could clearly see by performing these plots that there were discrepancies in the data, because a lot of the of the fetuses had a constant line, from early gestation to late gestation. And that really pointed out that, there's something wrong with the data, and you need to go back and clean the data. All right. So it was very helpful. So demonstrating these types of plots is extremely helpful in understanding what your data look like. And I'm going to see if I can try to demonstrate that to you with that particular data set. Now, it's also very important to generate cross-sectional plots of your data. It demonstrates patterns. These are data from the birth to 40 study, and it compares something that we call height deficit. All right. Um, and the patterns of height deficit over time, comparing different genders and different races. So you're looking at black females versus black males versus white females versus white males, all right? And given the history of South Africa, obviously, we know that there are differences in heights between the different ethnic groups, all right? And we know that white children tend to grow taller than black children simply because of the better economic circumstances to which they are exposed. And what these data show, for example, is if one is interested in a question of understanding how does height deficit change over time, you clearly see that white children do not experience much deficit in their lifetime in childhood, all right, between birth and 18 years. Whereas with black children, they experience a deficit, a increasing deficit in the early life period, and they also experience, particularly the boys, another deficit in the in the mid childhood period, what others call the foundation phase. So what these cross-sectional plots give you insight into, before you even start your modeling, you want to just see what the mean curve looks like. And this will tell you, at least when you see now the model, when you've modeled your data and you've generated a curve based on your model, you will understand that, what, it will tell you whether that model sort of follows the pattern of the data that you have in your data set. And the other thing that we see here is the differences in the standard errors. So the standard errors, they give us an indication of how precisely the mean estimates, the sample rather, estimates the population mean, all right? And with a larger sample, you've got more precision. As you can see in this study, we had more black children compared to white children. And as you can see, the standard errors here are much smaller, meaning that the mean in these groups of children is a more precise measure of the population mean. Whereas for white children, they've got wider standard errors, meaning there's a wider range, in which this value of this mean can be found in 95% of the cases. All right. So these are helpful types of summarizations that are important to perform before we even analyze and before we perform any longitudinal modeling in our data. I like this. So this is post modeling, and we're gonna deal with this in the second part of our of this webinar, which is tomorrow. All right. So you're also able to see by generating these individual plots. So what you see here in this particular slide, you see individual lines for the raw data, as well as the adjusted data, which is the data that has been modeled. So the colored lines, those are the individual curves which have been adjusted by the model to generate this mean curve, which you see in white here. All right. And through this model, we're then able to estimate individual deviation over time in term for this particular, for example, this is for weight. We're able to estimate the average deviation of every individual from the mean. So we're able to say that child A, grew on average 5 kilograms, was on average 5 kilograms smaller than the mean throughout this period, or was 5 kilograms heavier than the mean throughout this period. And those values are values then that we can use to analyze in other epidemiological studies. And that we, for example, if I'm interested to understanding what are the factors that drive the individual variations in weight, then you can extract those values that you obtain from this model and you apply them to that study, to that epidemiological study that one is interested in. It may not be, I mean, if you are in a different environment, you're not in epidemiology, it still applies, all right? Once you've modeled your data, then you can extract these random effects that we've generated to assess what are the factors that influence these random effects. All right, so I'm not going to go deep into what inferential statistics are, but just the important points in terms of how we approach our analysis when we're analyzing longitudinal data. So, for example, in our data set, we've got boys and girls. So we may be interested to see, as you saw earlier, the curves that I showed, where you've got a mean curve for boys and the mean curve for girls, or in the birth to 40 study, where you've got a mean curve for black females, black males, white females, and white males, all right? And you are able to then compare at each time point. So this is purely in a cross-sectional manner. You are able to compare at each time point whether there are differences in the means, all right? And this is helpful, to assess and to give you insight into whether there are huge differences, group differences in your data set, all right? And these comparisons can, obviously, we use something called a p-value, and we can test it at different levels of the confidence interval of confidence, which is at the 95% level of confidence, the 99%, and the 90%, all right? And the distributions it's important to understand the distribution, the underlying distribution of the data, so that you can know whether to apply parametric or non-parametric tests at this particular stage. And one of the tests that we perform, for example, if you're comparing groups, is what we call a t-test. And you'd be interested, for example, if you're dealing with two groups, such as your males and your females, you'd use the independent t-test. But also, it's possible to have two groups which have been matched on different characteristics, and that would be a paired sample. Or if you have measured the same individuals, and this is probably the simplest, the most basic method of longitudinal data analysis, because you've got individuals that are measured at baseline, and then maybe you introduce an intervention. Say, for example, you're interested in looking at individual weight before the weight of individuals before exercise, or some form of intervention. Let's say you're planning intervention to reduce weight, and you're planning an exercise intervention and a diet intervention and some other intervention. You want to introduce different interventions, and let's say you've got a combination. You've got one where it's purely diet, the other one where it's purely exercise, the other one group is both exercise and diet, and the last group is control, all right? Meaning you're not introducing any intervention. And you want to see whether these interventions will reduce the weights of these individuals between the two time points, all right? You measure them at one time point, and say you follow them up after 6 months to see what the impact of the intervention has been, all right? So in a way, that is a longitudinal study, because you've measured the same individuals, you've measured the same characteristic on the same individuals at different time points, and you're hoping that there will be a decrease in weight. So this is where a paired sample to test comes in. And this is what I was talking to earlier, when I was saying, when you're making these comparisons, it is possible that the differences that you see are because the means are different, all right? So here in this particular case, you've got a situation where the means are different, but the means are different, yes. So the mean for group one is much lower than the mean for the second group, but the distribution is similar. Now, it's important to explore this, because the assumptions of a t-test include the issues of equality of variance, for example. So if you are doing a t-test, you need to specify whether the variances are the same or not before you even run the t-test, all right? So you need to explore these types of plots. So, and where you identify that the variances are different, you need to then tell the program that you are using to analyze, to compare the groups, that I am dealing with a situation of unequal variances. If the variances are the same, then you are dealing with a situation of equal variances, all right? In this panel here, panel C, then you are looking at a situation where both the means as well as the variances are different. Now, just to end it off in terms of the different tests that one can apply for data, for the different types of variables that one has in their data set. All right. So if you've got ordinal data, if you're looking at correlation, for example, we're not going to look at agreement. Let's look at correlation as well as regression. And I think here, this is comparisons of groups. All right. So maybe let me start here because this is what we're talking about just now. All right. So you've got two groups that you're comparing. All right. The samples are independent or unpaired. Then, okay, you are interested in, so you, for non-parametric, you are, for parametric, you are interested in a t-test. For non-parametric, you can look at a Mann-Whitney test. All right. If you're looking at ordinal data, then you can compare the Wilcoxon rank test. All right. If it's nominal data, it's a chi-squared test. And if you've got more than two groups, all right, you are now in the area of ANOVA or Kruskal-Wallis. And also there is a format of ANOVA that deals with repeated measurements where you are comparing groups over time, different groups, three or more groups over time. All right. So I'm going to end here, and then I'm going to just quickly go to the R script as I end off. In the next part, we will do with part two from part two tomorrow, where we're going into the actual models that we apply in terms of the analysis of longitudinal data. And the script, the R script that I have here, it does cover the models, but that's what we'll deal with tomorrow. But the first part of this of the script deals with these explorations that I was telling you about. One of the it's not, what do they call them? One of the packages, sorry, that's the word I was looking. One of the packages that I really love in R is a package called CITA. All right, CITA is a growth modeling package. So it models child growth, and we use it in the best to 30 study to model height, weight, and BMI. We also used it in the Soweto first 1,000-day study to model your intrauterine growth. Excuse me, for the different characteristics such as your femoral length, your abdominal circumference, as well as your head circumference and biparietal diameter. And what I like about CITA is that built within it, it's got these functions that I was telling you about. So if we look at, for example, this data set, so I've got two data sets within this study here. So these are simulated data. All right. I simulated this data set called OBS, which is observations. All right. And it's got the ID, it's got the biological sex of the child, it's got the visit number. All right. It's got the age at that particular visit. All right. And there's a censoring variable here, which we're not going to talk about at this moment. We've got, okay. And we've got here, I'm not going to talk about this today, but here we've got the height of these individuals at the different time points. And then from this, I extracted just the key variables that we need, and I called it long data for modeling, and it's available here in my environment. For those of you that remember the different windows in R. So did I generate it? Okay, let me run that. Now it should appear. There it is. And if I view that, so I've got the variables that I need. Okay, so I've got the height. This is the rounded age. is and this is the the actual age, and this is the height of the individual. All right. So if, for example, I just wanted to explore this data, it's always good to know what the variable names are in a data set. All right. So here, for example, I'm not going to explore by gender. I could subset it and explore by child sex, but I'm just going to look at the whole data set, So I'm interested in the height. So this is my y variable here, and let me replace that there. All right. And here, this is my x variable, so it's going to be my age. And the dataset name is called long data modeling. Let me paste that here. In fact, let me copy and paste that there. All right. So if I load CETA onto my session, then I'm able, because these are specifically from CETA, so I can then run this for a plot. Oh, what is this? Okay, record ID. Let's see. We don't have record ID, we've got subject ID. It allows me to plot by individual. So let's replace that. So this is in real time, and which is why we see some of the challenges. All right. And it's good to see that. So you can clearly see, this is something similar to what I showed you earlier. You can see for this individual that there's a blip that happens, during their growth. All right. So they experience a decrease, and then they experience an increase. So you can decide whether that is a real value or it is an outlier. So for example, when I clean longitudinal data with this CETA function, which is plot clean, if I run that, it's going to plot for me these, and it allows me to choose a point that I consider to be an outlier. So for example, if this is an outlier, I will then click on that point, and this tells me the ID of this individual. So it's for this individual S066. So if I consider this, if I go back to my data set and I consider this to be an erroneous value, then I can make the decision that I'm going to exclude this value, only this value. It will only exclude the values that have been highlighted. It's not going to highlight other values. So for example, if I felt that this was also an outlier, I can highlight that. And this is for individual S002. And it's only going to exclude that point for this individual. All right, it's not going to exclude both points. So let me show you then what happens. So I always store the outliers because I want to be able to, for reproducibility and for transparency. If somebody wants to know what I included and what I excluded, I must have a record of the values that are excluded. And obviously, I must write and explain why I excluded those values. So I'm just going to call this store outliers. Okay. Store out, and I'm just going to call this outlier, and I'm storing it as a data frame. All right. So once I've clicked on that, I click finish. And so it's done now. If I click, nothing is going to happen. All right. If I'm clicking and nothing is happening, I can see there's another one here. I mean, if you look carefully, there's another value, there's another person who's experiencing a sharp decrease, all right, and then experiences an increase. That could be another outlier. There's another function within CETA that allows, because you can't see everyone, right? You can't see everyone. So if an individual, for example, you want to use you want a way of identifying individuals which experience these sharp rises or sharp dips. All right, and there's a way of doing that in SITA. I did not cover it today. Maybe I'll just demonstrate it quickly tomorrow before we get into the parts in the next parts of our of our of our webinar. All right, so I'm going to store this. All right, and I'm going to extract. So I need to remember. Okay, I don't know this off by heart, so I've got them stored in my other code. So let me just go to my recent files. So if I go to uh, I just want to find the way. Okay, so extract. All right, let me just demonstrate this first. So if I've got store out, so here it is. It's got two variables, two value observations rather. You've got the value in row 9 and row 263, and those are the values which are the age at which you have identified the outliers and the actual height values that are either outliers or they are true values, but they are small for that particular age. I'm just trying to find the the function that I use then to subtract these. I've got it in my other scripts. So I would, okay, so let's try this. So it will be, let's see if this is gonna work. So it's going to be that minus rows. No, minus, let's see, minus outliers, I think. Okay, minus row, those row names. Let's see. Let's see if that's going to work. Okay. So if I were to minus row, okay, let me, I'm gonna use a longer way to try and get this. Let me, so age, so I'm going to look at 66, for example. There's a quicker way of doing this, but I've sort of, yeah, forgotten the actual code that I use here. So row 1 is, so minus, so this is which equals to less, okay. So it's going to be that. Let's put that in brackets. Oh, what happened there? Let's put that in brackets. Minus which is going to be that minus which that ID subject is equal to, I'm just going to subtract this one, and longitudinal, I think this is age is equal to 10.66, 10.26. All right, let's see if it's going to work. I must put a comma there. All right, let's see. All right, so yeah, it's subtracted this. There were 404 observations. Now there's 403 observations. There's a much quicker way of doing this, subtracting them all at the same time. It's just that I have forgotten the code for it. All right. I will fix that tomorrow. So now we are looking at the new data set, and I always, as practice, I always assign this into a new data frame. All right, so that I can follow the steps that I taken. So the new data frame is now called long data mod 1. All right, I'm going to do the same thing to see to identify this, to identify whether this value has been removed. Okay, so if I run mplot, you can see clearly that that value has been removed. All right, and if I run the plot clean, it does not appear. Instead, it's this one, so that you can see what happens when you click on it. It identifies, it just highlights that trajectory of that one particular individual that has got an outlier. If I click on that one, for example, it also shows that one individual that has got a deviation. But like I said, there is a much more intuitive way of doing this rather than doing it individually. So I'm just going to pause there. The rest of the codes demonstrate what you saw in the presentation. So in R, you use ggplot to generate basic plots. So this is a plot that we generated, the scatter that we saw earlier, which is the scatter plot. And as you can see, here's the plot, and this is the line plots that I demonstrated earlier. And there are different ways of you can use DPLYR deploy to summarize. Another one is called I think it's RMISC, where you can summarize the data to get. So if, for example, I run, what time is it now? Okay, I need to stop. If I wanted to summarize, generate a table with the summaries for these groups. So I can, if I run that, it should show me cross means, all right, and it shows me the means for the boys, and it shows me the means for the girls, the mean and the standard deviation, and the sample size and the age, the rounded age at which those data were collected. So I'm going to stop there for now. I've just demonstrated some of the ways in which you can describe data, longitudinal data, in preparation for running your modules. So tomorrow, we're going to look at an introduction into linear regression before we then get into how we analyze longitudinal data using mixed effects modeling.